My name is Dr. Clement Nka. Today I'll be talking about the process of infection with HIV. What happens subsequent to the infection? First of all, there are 4 barriers or 4 defense mechanisms that our bodies have. The first one is the anatomical barriers. You know, the anatomical barriers like the skin, like tears, like saliva, to name but a few. And the second one is the intrinsic defense system. I'll be talking about that. And the third one would be the innate immune system. The fourth being the adaptive immune system. Those are the defenses. But now we want to look at HIV. What happens? First of all, if you get infected with HIV, the second defense mechanism becomes operative. The first, the anatomical one, doesn't really help. The second defense system becomes operative. Once you are infected with a virus, the normal defense mechanism is what is known as APOBEC. APOBEC tries to change the genome of HIV. We know that HIV is actually an RNA virus. So it tries to change it. What does that mean? To change what? To change the nitrogenous bases. The nitrogenous bases, we're thinking of the GC, guanine, cytosine. We're thinking of AT, adenine, thymine. Now, we have just one row of those. If you change one of them, the HIV virus, the genome is no longer HIV if you change it. We call that mutagenesis. There must be a mutation, a change of one of these nitrogenous bases. For instance, the normal one is to change maybe a T and you make it a U. That is uracil. You put uracil. Then it doesn't become HIV anymore. So if you do that successfully, then HIV is toothless. It's like a toothless bulldog. It's not gonna hurt anybody. But the problem is the virus itself. The virus itself has got a counteracting mechanism, has got a protein that goes against this mutagenesis, because this change of a nitrogenous base and making it something else, taking instead of a T you put uracil, you know, all that is counteracted by HIV itself. How does it counteract it? It uses a VIF protein. So if we could go against the VIF protein, unfortunately, research has not yet been done to counteract the VIF protein, but this is the VIF protein that makes sure that the mutagenesis is not successful. So in the presence of the VIF protein, HIV will be able to get in and it will get established in our bodies. Secondly, when we are infected with a virus, the defense mechanism is that of the development or the formation of an interferon. Interferon goes against this infection, the viral infection. So HIV, so to say. Specifically, it has got a specific interferon. They call it tetherin. Tetherin will keep HIV on the surface. In other words, it won't be able to get in. It's kept by the tetherin interferon. So it keeps it there. But each attack has got a counter-attack by the virus. The virus counter-attacks the tetherin, this interferon. It actually blocks the entry of HIV. So it has a special protein. They call it the VPU protein. The VPU protein counteracts tetherin, and then HIV goes in. So let's talk now about HIV being successful, going in. What should we worry about? I think we should worry about certain genes. These genes are in the HIV itself. These are genes of HIV. The first gene is the envelope gene. We know that from any gene, a gene will code for the synthesis of a protein. So the envelope gene, what does it code for? It codes for a protein known as GP160, glycoprotein 160. That's the protein. 160, which will be cleaved to become GP120 and GP41. It's 41. I don't know why they call it 40, because 40 plus 120 would give 160. So, but then it's GP41 and GP120. GP120 is the one that ensures that HIV gravitates to a particular receptor, a receptor that is, there are two types of receptors which are on our immune cells. The immune cells we're talking about this CD4 T lymphocyte. CD4 T lymphocyte has got two receptors, and these receptors, CCR5 and CXR4. So HIV being a tropic virus, it will gravitate to one of these, CCR5 or CXR4. It will gravitate because it's a tropic virus. It's a tropic virus. It's a tropic virus. It displays a lot of tropism, right? So it goes straight. It will go straight to that receptor. So it will use the GP120 to attach itself onto this receptor, which is the receptor of CD4 T lymphocyte. Attaches itself. But what is the function of the GP41? GP41 is responsible now for the fusion of this HIV being fused to the immune cell now. The immune cell, the actual CD4 T lymphocyte being fused. So the fusion is done. Attachment is done by GP120, but the fusion is done by the GP41. So if that happens, then HIV will be able to enter the cell. So that was the function of the envelope gene, produced the 160, which got cleaved to become the GP120 and GP41. Right. The second one is the gag gene. The gag gene, remember, any gene has got to be translated to become a what? A protein. Transcribed and translated to become a protein. So which proteins are we thinking about from the gag gene? We're thinking of the capsid proteins. The capsid proteins. And there are two types of these capsid proteins. There's the P17, which is the nuclear capsid. And there's the P24, which is the viral capsid. Man, this is now important because this is the one which is targeted by our new drug of choice, the injection that we're talking of, the lenacapavir. The lenacapavir is an injection. It goes against the nuclear capsid, that is the P17, the nuclear capsid. It goes against that. It inhibits it. It inhibits its formation. First of all, what was the function of this nuclear capsid? Nuclear capsid it protects the genome. It makes sure that it makes sure that there's a conversion of RNA to a DNA. Why is this? You remember, HIV is an RNA virus. So RNA by itself can never code for a protein. Oh well, no, for a protein. The central dogma of molecular genetics says DNA, RNA, protein. So it has got to go back to a DNA so that it can get a template as to how it's going to synthesize the viral proteins. And we will see right now how is this going to be affected? It's going to be affected by the Pol gene. The Pol gene. You've got the gag. The last one is the Pol gene. So what does it code for, the Pol gene? Pol gene codes for all the enzymes that we need to synthesize this DNA. In fact, the reverse transcriptase. It is the one that is responsible for conversion of RNA to DNA so that we can have a template as to how we're going to synthesize the viral proteins. And this is sad because the patient is a sufferer when it comes to this, because if those viral proteins are made, it means the virion, the HIV virion is a possibility now. So if with the presence of reverse transcriptase, and of course, if the Pol gene is translated to become a protein, it's going to become reverse transcriptase. It's going to become the aspartate protease. It's going to become the integrase enzyme. Remember, when it is formed, this reverse, when the DNA is actually formed from reversing, now the reverse transcription is now a possibility where you are reversing RNA to become DNA. So now DNA, we have now the DNA, and the DNA has got the template for the formation of what? Of viral proteins. So now we are capable of making the viral proteins. But how do we do that? We've got to have, so the DNA is given a special name. This is a viral DNA. A viral DNA. The viral DNA has got, by itself, remember HIV, is a parasite. It has to use the machinery of the cell to synthesize these proteins, though it has got a template. But that template, this is how to make the proteins. These are the proteins, and what? But still, it's not capable of making them. It has got to make sure that it uses the machinery of the cell, the host cell. That is our cells. The host cell. It has got to get that machinery to work. How will it do that? It has got to go to the nucleus. To get into the nucleus, it has got to be integrated into the cellular DNA. This integration is done by a specific enzyme, that is the integrase enzyme. Remember, if the Pol gene was not there, we wouldn't have the integrase enzyme. We wouldn't have the protease, aspartate protease. We wouldn't have the reverse transcriptase. Reverse transcription is a possibility because of the presence of the Pol, or of the Pol gene. Pol gene was translated to become a protein, to all these proteins, that is reverse transcriptase, which made it possible for the formation of a DNA, viral DNA, which is now going to have the template to synthesize the proteins. But now still it can synthesize the proteins. It has got to be integrated into a cellular DNA. It has got to go into the nucleus, so to say, to find the cellular DNA. The cellular DNA then it gets integrated into the cellular DNA. And that, once it's integrated, then that cellular DNA is capable of replicating, making copies. Then it generates billions of copies. And this is an unfortunate set of circumstances for the patient. It is an unfortunate set of circumstances. That's why we have to come in with our antiretrovirals and to make sure that we have been using. Now, we have a preventative way. We are going to give the lenacapavir injection. We'll give it for 6 months, all 6 months, and then give it again, and it prevents, because it is an inhibitor of the capsid. It's a capsid inhibitor, and so it goes against, so to say, our gag gene. Our gag gene, it will go against, the gag gene will code for capsid proteins, both proteins, that is the nuclear capsid and the viral capsid. But then specifically P17, it will go against that. That is lapin. It will make sure that the viral, the genome of HIV is not protected. It is not protected. It will be protected for as long as there's a capsid, a proper capsid, a nuclear capsid, and a viral capsid. But this time, we are at an advantage now. We have lenacapavir. Give it for 6 months as a preventative therapy. And we give it to people who are confirmed to be HIV negative. In other words, tests have got to be done. There's a rapid test, and there's the test to test whether the patient is positive for HIV or not. Check. If it is established that the patient is negative for HIV, then that's a very good candidate to prevent the infection using lenacapavir, which is a capsid inhibitor. All right. So this, we have to make sure that people are negative for HIV. Again, even if patients are positive for HIV, If they are taking their treatment well, that is the normal ART, antiretroviral therapy, and make sure that they, if you're taking it, the tendency will be to be undetectable. The viral load will be undetectable. And undetectability, we always say it is tantamount to what? To untransmissibility. Untransmissibility being equal to undetectability equaling to untransmissibility. So this patient who is like that is still a candidate for lenacapavir, and lenacapavir injection, which will be given for 6 months. And then after 6 months you get another shot. So this is actually if we know what we're going against, we know that this time we're targeting our nucleocapsid, making sure that there is no protection of the genome, of the HIV genome. In other words, the possibility of in reverse transcription, it will not be there, because number one, there was no, remember, where does the reverse transcription take place? It takes place in the nucleocapsid. If the nucleocapsid is not formed at all, what's going to happen? So this is a problem. So the reverse transcription is going to be a problem. Remember, the nucleocapsid, if it is dissolved, then you're not giving a chance to the to the Pol gene to produce its enzymes, like reverse transcriptase, like aspartate protease, like integrase. So you're not giving it a chance. Protease, I'm not mentioning too much, because protease works whenever you have succeeded in making the virus has got its virion. The virion is already there. It's just that the virion is clumsy, having its appendages, and then those appendages are chopped down by the protease enzyme. So we don't even get there. At all. We're using 2 genes. The envelope gene, which will give you your GP160 being cleaved to become GP120 and GP41. And so it ensures the attachment. Of the GP120 to maybe CCR5, maybe CXCR4, because this is a trophic virus that will gravitate to a particular receptor. It will gravitate to that one and then gets attached. And then GP41, making sure that there's fusion between the 2 enzymes, between the 2 cells, the HIV and the immune cell. Thank you very much. Thank you very much for listening to me. This makes a lot of sense now that South Africa is preparing to give the lenacapavir injection. It makes a lot of sense as a what? As a capsid inhibitor. Thank you very much.